Hi, Assalamu alaikum. This is Mohammad Shahir Shoykot, and thank you for choosing me as for phase two. So in phase two, I need to solve these four tasks. Okay, so I am making this video for to solve these four tasks given by the data in this. So okay, let's begin with the first one. So in the first text, I need to solve that. There is a question that outline an algorithm for finding a minimum spanning tree in a distributed systems, and I need to give a follow up in what real world ML scenario would I use MSTs. So let's discuss. Let's draw something and discuss with it. So where's my pen? Okay. Mm, okay. 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 Right. It's working now. So for the question one, and we know in a distributed systems, finding a minimum spanning tree like MST involves computing local MSTs on such subgraph like partitioning across the servers, and then uh, iteratively merging them to the from the global MST, and each of the server first applies a standard MST algorithm like Kruskal or Primes on its local data. Um, then the neighbor servers communicate with the minimum weighted ages, connecting their subgraphs, merge their local MSTs, and repeat this process until all the subgraphs are connected into a single MSTs. Like algorithm like Gelger, Hamlet spires, or the Borg's algorithm are commonly used for distributed MSTs compilation. Like if I draw a diagram of MSTs, okay, diagrams, then here will be the subgraph of A, like it's the MST of A, and then subgraph of B, like MSTB, okay, MST of B, and then subgraph of C, like MST C, and then with the minimum ages, like minimum ADG ages, and then adding those all the three ages with a global MST. So global MST, and each of the block represent a local subgraphs handled by one server, because it's a global servers, and local MSTs like MST A, MST B, and MST uh, Cs are computed from the local, and the minimum weighted ages connected to the subgraphs are exchanged to the merge local MSTs into the global MSTs. Like here is the minimum weighted ages, OWA weighted ages. Okay, so this iteratively merge continues until the subgraphs are all the subgraphs are connected to each other. Okay, so if I give a follow up for these textures, so uh, basically MCs are useful in the machine level, like sensor network feature selection, like connect sensor with the strongest correlations, then select the respective sensor from the each of the ML model. And on the other hand, hierarchical clustering, so use MST's ages for single lines clustering. Okay, so and the other hand, apart from these hierarchical clustering and the sensor word features, so we can use the anomaly if we need any detect the anomaly. Then large weighted age in the MSTs often indicate rare or anomalies collections. So with the large weighted ages, we can say this is anomaly. So for example, in an IoT systems with 1000 temperature sensors, like MST can help pick a subset to sensor that represent the entire network efficiently, or reducing the features of our ML models without the losing of those informations. So I guess uh, for the little description, I guess this is for the question one. So now moving on to the part two. Okay, give me some time here. Some issues are occurring. Okay, okay, okay. This is for part one. Let's say part one means question one. Okay, Q1, and here is the part two. This is for question two. So let's have a look that what is asked for question two. So given a large stream of the user interactions, design a structure for order of online login, order of login. So ranges some queries and updates supporting both extent and approximate aggregation for downstream feature generation. And for this question also there have an follow-up that how would I parallelize the update for distributed feature stores. Okay, for part two. Okay. For part two, so we basically on we all know that in real world scenario, when we have the massive volumes of users data, such as the click streams or the e-commerce interactions or the social media activities in the Facebook or Twitter on the Instagram, so it becomes extremely important to quickly calculate the total sum within a specific range of and update the value of value in efficient way. So for this, we can use a Fenwick tree, also known as the binary index tree. It's working like the binary tree, but not the exactly same as the binary tree. So this data structure allows us to handle the large data efficiency using very little memory. We can gain the range of some order for log n time, and we can update the user of interaction also is out of log n as well. So and if we need the approximate aggregation, like we can divide the data into smaller segments. Like if it is data, we can segment like this. So use sampling or quantization, which speed up the features generation even more. So in this distributed systems, basically when multiple workers nodes are updating data simultaneously, so we use sharing or the segment wise parallelism. Each hard maintains its own tree, and then the result are combined in a global aggregation steps. Like if I draw a tree, like this is a dummy of root, and then this is a 2, and then 3, 7, 1. So there are also some child also, 4, 6, 13, and then 13. Okay, so if I drag some right, okay, so let's drag some left. Okay, okay, correct. Okay, so if Fenwick tree mainly stores the prefix of the sums. So but in a compact way, the tree is structured so that we can perform queries and updates in the logarithmic times. For example, if you have these Fenwick tree array like index 1, 2, 3, and 4, and then 5, the this is the value of index, and the width value is 3, 5, 1, 10, and 5. Okay, Okay, so here there will be one thing is 1, right? 2 means there will be the bit value will be 5. 3 means the 1 is okay. Let's say I didn't give anyone. Okay, let's say I hear 1 and then 3. Okay, so 3 means 1. Okay, 4, there will be 4, no 4. Okay, let's say 4 is there, so the bit value will be 10, and then 5, let's say it's 5, and the bit value also will be 5. Okay, so here's the bit I represent the prefix sum of the specific range, like uh, bit value is I. That's mean it will increase the 1 by 1. Like in step 2, the suppose we have some one sum 1 to 5. Let's say we need, or we calculate that the sum from 1 to 5. For that we start from I is equal to 5. Okay, and then repeatedly do the same thing again and again, and we are using the formula will bear y is equal to I minus I and minus I. This is the magical of the bit. Like firstly it will, if I give the example of the how it will be calculated. So it will be calculated like, firstly the sum will be 0, and then I is equal to 5. The sum now it will be bit value 5 and is equal to 0. So the sum previously the sum was 0, and then now when 5 comes, so sum is equal to sum plus 5. The next answer will be 5. The next sum will be 5. And then let's say when the formula is came, then I is equal to 5 minus 5 and minus 5. It's basically 4. Okay, okay, then we get the I value is 4. Okay, if I drag right side, so let's say I is equal to, for now I is equal to 4 because of we got it from there. So the sum will be sum plus uh, bit value of 4 by index 4. So the index 4 is equal to is 5. Okay, 5. So previously the value, the sum was 5, and then the index number 5 is the bit value carrying 5. Okay, so for now the value will be 5 plus 5 is equal to 10, right? Okay, and for these we can calculate all the sum from 1 to 5 easily. For this section, for this part, if I give some follow-up, so to parallelize the update in a distributed failure store, I would share the data, for example, by user or time. Each shared would have its own Fanuc tree, allowing multiple workers to update in the parallel without conflict. Then a global aggregator merges that there's these local trees periodically to keep everything consistent. So yes, and this ensures the low latency and high throughput for real-time ML features or real-time ML production level work. Okay, so let's move into our question 3. Okay, question 3 in part 3. Okay, so you were tasked with designing an ML model cache, like explaining how Splay trees helps the optimize the access pattern and what the trade-offs are compared to the LRU cache. There are also a follow-up question that when it's displaying the harm latency in serving predictions. Okay, so for this, um, okay, let's see here. We're going to answer the question part 3. So it's like it's not the it's more like a theoretical answer. It will be a theoretical answer like uh, a split tree optimize ML model caching by automatically moving access model to the root through rotation. So we frequently use the model natural stay at the top of the near constant access time. So for this reason that this is the perfect ML serving where the access follows power laws distributions, and if we 20% of the model handle 80% of the traffic, like trending recommendation or the popular language model, those who a model cluster near the root achieve order of log n. Okay, and yes, out of login and optimize the access that approach order of one, while cone model gives to leaves and uh, basically uh, however it's compared to the LRU cache the trade-offs are significant. Like in LRU it's guaranteed that the order of one access always the via hash tables, and while splay trees have order of login but average but order of login outs in our outs cases. So critically splaying requires the exclusive logs that prevents concurrent reads, or whereas the LRU allows the parallel access through log stripped buckets, and LRU is predictable with the deterministic latencies like splay trees are available for upgradable. So this is for the part 3. This is based on the theoretical also, and let's moving into the part 4. So here comes the question is build a system to support efficient merging and querying of a connected user component in a social graph as A's are added or deleted for clustering in ML follow-up. How does the union by rank and path comparison is paid by large scale of ML operations? So for this, for in these steps, we I basically build up a system which from there we can give the all answer to you. So let's move into our or let's showcase our project for the question 4. So here are the part 4. So we have to launch the application first. So let's launch that application from Visual Studio Codes. So yes, it's just a Streamlit apps for the basic UI UX. So when the app launches, then it will on localhost 8501. It is not hosted, so it will run in the locally. So firstly, in the left sidebar, you can see there is a number of nodes user. So we can use any sort of nodes, like any number of nodes. Like it will be at the max portion is 100. And so let's say let's create a take a node at least 10, and then click with the initialize graph. That's mean the total nodes is 10, and the total component will be 10. Okay, and the edges will be 0 because of we didn't connect any edges in all the nodes then. So okay, so in the part 2 it's friendship edges. That's mean we call it friendship edges means in the two nodes there will be some edges or the some relations. For the user one, if we take the value is 0 from the 0 node, we all know that when we create any graph or sort of things, we took it from the 0. Okay, and then we increase in one by one. So for the first user, we were taking 0, and the user second we are taking 1, and then connect. If we connect that, then there will be a message that connected user 0 to 1, and there will be 0 to 1, 1 to 2, and 3 to 4. Okay, so when we were connect that 0 to 1, 1 to 3, 2, and 3 to 4, let's say that in the look at the sidebar. So the total number is 8, but the total component will 9, because of the two edges, two node is connected with one edges, right? So okay, and there will be the edge count. Okay, and then if we added, like say 3 to 4, 3 to 5. Okay, so connect edges, and okay, so like let's say it's counting. Okay, it's counting like it is 2. That means and another two nodes are connected with another new edges, right? Okay, and the next part is the query part. It's like a great website. Like if we check the connections, like why I can check. Okay, let's say user A is equal to 1 and user A equal 2. Let's if the connection is user 0 and user 1 are connected. Okay, so here we can see that which those nodes are connected each other with the different kinds of weighted edges, right? Okay, so for the check connections, okay, for the check connections, we can check the connection between the two nodes. Okay, and the find component. Okay, let's say if I have the user ID is 0, and then let's say find the component. Okay, so 0 belongs component with rooted with 0. Okay, the component number is 0, 1. Let's say do remember that in the first pages when we were taking the add edges, where we added 0 to 1. Okay, okay, and then here we can also also calculate the component edges. Okay, component sizes, like here the component level of number was 10, but when we use the 4 nodes and the 2 edges, then the edges number will increase and the component number is decreased. Okay, okay, for the visualization we can check that let's say that 5 to 4, it is connected. Okay, some edges, if I zoom our screen. Okay, and then 0 to 1 is connected. Okay, so and then here you can see the 0, 1, 1, and 4 or 5 are connected each other. Okay, and then performance sense is we can the benchmark. Then there will be the naive bias order login with the 100 millisecond is executed, and then union by rank is at 6.64 milliseconds, and full the optimization is 0.64. Quite good. Okay, so okay, there's the learn portion. I have just put out some sort of theoretical things to get the better knowledge from it. So okay, that's it for today, and thank you for giving me the opportunity to explore all the things in my phase 2, and I look for with collab with all of you, and I'm eager to take the knowledge from you all. And thank you for guys, and assalamu alaikum.